A few terminologies before we get into the proofs. An axiom or a postulate is an underlying assumption about that we are going to make. Now, sometimes axioms come from the real world. Sometimes we just make those up because we want to work in a certain uh, domain. So, for examples of axioms could be things related to, say, why triangles are equivalent. Axioms could be about numbers. You could have an axiom of what does it mean for a number to be prime. You could have axioms about what does it mean for a number to be even, things like that. We always need to be careful with the axioms that we work with, because if you start with an axiom that is incorrect, then the proofs that you come up with would be incorrect as well. Then we have rules of inference. We will look at how we can design these rules for inference. And essentially, the way to think about rule for inference is we can take a tautology that is of the form x implies y, and we can convert that into a rule of inference. A proof is a sequence of propositions where that forms a valid argument. And fallacies is where we do something that is incorrect, resulting in an incorrect proof. A couple more things about terminology. A theorem is a proposition that can be shown to be true. Lemmas are simple theorems that are used to prove other theorems. Corollary is things that follow from previous theorem or lemma. Conjecture is just a statement that we have made, but we are not sure whether it is true or not. Technically, all these three things are same, in the sense that if I prove something as a lemma or a theorem or a corollary, it has the same level of meaning. The difference comes in terms of how much weight do we assign to it. So, in some sense, theorems are things that we care about, things that we want to prove. Lemmas are things that we will need in order to get there, but the lemmas by themselves may not make much sense because they're just statements that only later, when we figure out how to use it, makes sense. And corollary is something that we use when we want to say, well, I just proved this thing. Well, what is the logical implication of this? That's what we'll call corollary. Conjecture, on the other hand, is completely different. It is saying something which we don't know whether it is true or not. So conjecture is just a statement. We often make conjectures when we think a particular statement is likely to be true and we want to build on it for some reason. And that's one of the places where we do use conjectures. Rules of inference are used to deduce conclusion from hypothesis. So these are logical implication questions in which the answer is yes, and we have already verified that the answer is yes. So let's look at this question. Does P and P implies Q? Does it logically imply Q? Now we can do this by a lot of ways. We can see if this formula is a tautology. If we verified that it is a tautology, we can create a rule of inference from it. Now in this example, the rule of inference that we have is called modus ponens, and symbolically we write it like this. So here we have P implies Q, and therefore Q. So what does this mean? This means if I have a proof where somewhere I have the formula P, somewhere down here I have P implies Q, then I can use these to write the formula Q. Here are a few tautologies. I want you to verify that these are tautologies by writing the truth table. Now we are going to prove, we are going to use these tautologies to come up with some rules for inference or rules of inference. So I want you to first focus on just these two. Just remember these two as we go along to the next slide. So the first one is P implies P or Q. The other one is P and Q implies P. From these two tautologies, I can create some rules of inference. And the rules of inference that we have are these two over here. So here we have, if P is true, then P or Q is true. And the reason we could do that is because P implies P or Q is a tautology. Same way, P and Q logically implies Q. P and Q logically implies P, and that's because this is a tautology. The rest of the things that I have on the slide, this slide as well as the next slide, are essentially the tautologies on the previous slides. I have converted them into rules of inference. What I want you to do is verify these rules of inference by comparing with the previous slide. The same thing for this slide. These are rules of inference that are derived from the tautologies that we had earlier, and I want you to look at each of these and see why these are valid rules of inference. Next, we are going to look at some rules of inference for quantifications. So we have four rules here, and they look somewhat similar to each other, and therefore I want to focus on two of these rules specifically, and the other two rules are similar. So let's look at these two rules. So the first one says, for all x px, if I have proved this, then I can conclude that P of C is true for any C. The third one says, if I have proved that there exists x P of x, then I can conclude that P of C is true for some specific C, but we don't know what that specific C is. So let's try to look at an example. Let's consider that the property that I want to prove is, let's suppose that the property that I have proved is for all x, and the domain in this case is the people in this room. Let's suppose I have proved that for all x, the person is more than 10 years old. Now I can conclude that I can choose any person in here, and that person I will call it C, and that person is more than 10 years old. So here we get to choose C to decide what that C is. Let's look at over here. Let's say that the property that we are interested here is there exists x p of x, where p is, say that the person was born in, say, Paris, France. So let's imagine I have proved that there is somebody here that was born in Paris, France. Then I can say that there is some C that was born in Paris, France. Now I don't get to choose who that C is. It's just that there is some C, I don't know which it is, but that person was born in Paris, France. Now what can I do with this? Let's suppose I wanted to prove that there exists a person that was born in Europe. I can say, well, I know that there is somebody born in Paris, France. That means there is some C that was born in Paris, France. Now I can say that, well, if that person was born in Paris, France, that means he was born in Europe. And then I can use this last rule where I have said that I have shown that there is some specific person that was born in Europe. So I can say that the property that exists x p of x, where p says the person was born in Europe, is true. This second rule is for universal quantification. So let's go back to our previous example, and let's say that the property that we are looking at is everybody in this class is more than 10-year-old. So in that case, I could say, well, choose any C. That person is more than 10-year-old. Now from there I could say conclude that the person is more than 5 years old. So if my property P was the person is more than 5 years old, then I have proved that no matter which C I take, that person is more than 5 years old, and therefore I can conclude that for all x, the person X is more than 5 years old. So these are the rules of inference for quantifications. One allows us to remove or add universal quantification. Those are the rules over here. And we have these two rules that either allow us to remove a universal quantification or add a universal quantification. And we will need to use them as we go along in different proofs. So I'm going to introduce the notion of a proof tree. So far, we have been thinking of the proof as a straight line. I start with a bunch of hypotheses, bunch of tautologies, and then I simplify it to figure out whether the conclusion is true. We could also think of the proof in terms of a tree, and the reason it becomes a tree is because we can partition the proofs often in terms of cases. So one example could be, we could say, well, I have two cases, either P is true or P is false. So in one case I have P is true, that follows a path of the proof. There is another path where P is false, that follows another path in the tree. We could take this further. We could have more than two cases. So here we have case 1, both P and Q is true. Case 2 is P is false. Case 3 is Q is false. And in each one we are going to come up with the proof ourselves. We will not study this explicitly because it's not something we will need to do in this class, but as later on in subsequent courses, or if you are getting into this in this field where you will be writing proofs uh, for your schoolwork or anything else, you may need to use proofs that are of this type.
Once again, we have reached the check before you proceed slide. Be sure that you have understood the rules of modus ponens, universal or existential instantiation, universal or existential generalization. These will show up in most of the proofs. The others mm, don't show up as frequently, but depending on the proof that you're looking at, the other uh, parts would show up as well. The universal and existential instantiation looks very close to each other. However, there is a difference in that in the universal instantiation, the C that you get can be anything, whereas in existential instantiation, it has to be something specific. Uh, Make sure you understand the difference between these two, and if not, please let me or TA know and we can go over it more. The key difference is if you got the C from existential instantiation, then it is some value in the universe of discourse. You can't add more constraints on it because those constraints may not be satisfied uh, by that particular C. So for example, if I had said there exists an even prime number, uh, say, well, that is true because 2 is an even prime number, but then you can't add a constraint on that saying that, well, I want it to be greater than 17. That is not something that is possible. You should keep copies of the tables from the previous couple of slides with you during exams. This is true even if exams are supposed to be closed book otherwise. We will have more examples in the next module of proofs, and so you can go ahead to that after you do the review quiz for this module.